Wait till November.
Yeah, it's getting worse. So I don't know. Um, okay, so let's talk diffusion, guys. Right. So we talked just a little bit about vacancy diffusion. We did um, some really fundamental stuff with when we talked about interstitial diffusion. And I want to reiterate that even though we're talking about this in the context of interstitial diffusion in metals, really what applies there, this is true for the general theory works for glasses, liquids in the absence of convection. So the fundamental notion of an Arrhenius temperature dependence on a diffusivity, right? Fix first and second laws and the general form of those equations that we looked at in the general solutions, right? That if something is concave up, the concentration is going to increase. If it's concave down, the concentration is going to decrease with time, right? These are really fundamental things that apply across all systems, not necessarily just interstitial diffusion in metals, right? So today the slide deck is called vacancy diffusion, but we're going to talk about other defect-mediated diffusion mechanisms in ceramics, right? And so, this again, and you'll see this pattern follows. The equations look really much the same. So let's sort of jump into it. We'll start by talking about self-diffusion, right? So self-diffusion means essentially A and A, but the key difference that we need to talk about here is that in interstitials, the diffusing atoms were always surrounded by other vacant interstitial sites. So that meant the jumps really could happen whenever the interstitials had enough energy to overcome the energy barrier for migration, or delta GM, right? Now we're in the regime where the atoms can only jump if there is a vacancy next to it, right? On Monday, we'll talk about diffusion in mixtures. It gets a little bit more complicated, and we'll see why. But so let's talk about self-diffusion, right, of A and A. So experimentally, we can measure it by by doing an experiment called tracer diffusion, where we introduce radioactive atoms, A atoms, into A, and we'll call those A star. And since A is chemically identical to A star, their jump frequency is going to be identical. So the diffusivity of A star is going to be equal to the diffusivity of A. All right. So the probability of making a jump is going to be proportional to the number of vacancies, right? So this is just the equation we saw before multiplied by the fraction of vacancies, right? So this jump frequency for vacancy diffusion is much less than interstitial diffusion, right? Because the number of vacancies, unless you're up at close to the melting temperature, is very small. Remember, you calculated the equilibrium number of vacancies as a function of melting temperature. So if we're low, right, this is going to be a small number, right? All right, we have our Boltzmann statistics. So if we combine it, we get this term. Oh, shoot. Oh, no, never mind. I thought I made a mistake here, but it's not. Right, so if we combine this, we have the diffusivity, and the energy barrier for diffusion then is the delta G of migration. So remember what goes into this delta G of migration, right? That's essentially the lattice distortion that you have to do to move an atom from one place to another, right? When you hop an atom, you don't have a nice clear path. You have to move some other atoms out of the way to be able to get into there. Plus, the Gibbs free energy associated with a vacancy formation, right? And so this is going to be the overall, right? And so we separate it and we move the entropy terms out and we have just the enthalpy terms here. We do a little bit of rearranging and we end up with a form that looks exactly like what we have for had for interstitial. Our diffusivity is equal to some d naught, and then we have a term that's exponential with respect to some activation energy, right? And this activation energy is just the sum of the enthalpies, right? So for a given crystal structure, this ratio at the melting temperature is going to be approximately constant. So therefore, we can say that the activation energy for diffusion is going to be pretty proportional to the melting temperature, right? So what this tells us is that we can do some pretty powerful approximations by just normalizing the temperature by the melting temperature, right? This is called the homologous temperature of a material, right? And so then the diffusivity for a given crystal structure, so all FCC crystal structures, all materials that have FCC crystal structure, all the materials that have BCC crystal structure, all the ceramics that have the same lattice, right? So everything that we talked about for simplicity, we talked about being on the rock salt lattice in terms of ceramics. All of those, if we normalize the temperature by the material's melting temperature, the diffusivities are going to fall on about the same line for making good approximations, right? So this really shouldn't be surprising because we already know that the melting temperature is going to scale with bond strength, and so is the activation energy for diffusion, right? The enthalpy of diffusion. So it shouldn't really be surprising that this kind of relationship comes up, but it is nice. Right. So here we just sort of have some the diffusivities and some data broken out by classes. This is just sort of right from the reading. What we just sort of interesting is we want to look at the general scaling of this, right? So here's our activation energy normalized at the melting temperature, right? So this is the diffusivity close to the melting temperature or at high temperatures, right? And notice that BCC metals have the lowest activation energy, right? Right, it kind of makes sense, more open structure, right? So diffusion is going to be faster here, right? Notice that FCC metals and HCP metals are here. So in general, metals are going to have a faster diffusion rates than other solids, right? So graphite here, why does graphite have fairly fast diffusion compared to diamond? Right? I mean, diamond, this has the slowest diffusivity rates. Right? The layers aren't connected, right? So we have essentially van der Waals forces holding the individual layers of the graphite structure together versus strong tetragonal sp3 covalent bonds, right? And the other thing with graphite is those of you who study things like solid oxide fuel cells and batteries and do other electrochemical type work, you'll know that the solute atoms can move in between the layers of the graphite structure, right? So we've got sp2 hybridized carbon, right? And so then if we look, generally we see our oxides, right? So alumina has forms a protective barrier on aluminum, right? And that's why aluminum doesn't corrode nearly as fast as the electrochemical potentials would seem to indicate, but it's not impervious, right? You can still diffuse things through the oxide, and in general, that's how the oxide has to grow, right? You have to be able to diffuse oxygen through your oxide layer, right? You have to grow from the metal out. Carbides, trigonal ice, olivine is an interesting geological material. But anyway, this just gives you the general trends that metals are going to have the lowest activation energy for diffusion, ionic ceramics, and then strong covalent ceramics, right? Ice is a little interesting here, right? So if we think about this diffusivity a little bit, one way to look at vacancy diffusion is we can talk about atoms hopping into a vacancy, and we can look at how fast those atoms hop, right? We can also, hold on, I'm gonna finish off the attendance, right? And if we think about vacancy diffusion, we can think about atoms hopping into the vacancies. And we can ask the question, how fast do the atoms move through our solid, right? Normally, when we're talking about diffusion, that's what we really care about. I want to know, how fast does element B move through A? The other way of looking at it is, how fast do the vacancies move around, right? So it should make sense that if an atom can only move if there's a vacancy next to it, but the vacancy moves every time an atom hops into it, that the vacancy is going to move much, much faster than the atom, than individual atoms. Most of the time, the atoms stay still, but the vacancies are hopping all over the place, right? And we can actually think about it from a logical point of view, that the diffusivity of the vacancy, right, times the number of vacancies has to equal the diffusivity of the atom, right? Because if I only have one vacancy, right, that vacancy is going to move around, but the atoms are essentially going to be completely stuck in position, right? So this relationship is going to hold most of the time. The volume fraction, or the atomic fraction of vacancies, is going to be quite small, right? So that our atoms move at a much lower rate than our vacancies. Our vacancies are hopping all over the place like crazy, right? So I talked about ionic solids before in terms of diffusivities on the previous slide, right? And we talked about Shotkey defects on a previous homework assignment, right? Saying that these are pairs of vacancies that form to make way for charge neutrality, right? Individual vacancies in ionic materials is pretty rare because you have to maintain charge balance, right? So generally you're going to form coupled pairs of vacancies, right? So that locally my charge balance is off, but globally it works out, right? And so instead of being mediated by single vacancies in ionic ceramics, you can have Shotkey diffusion, where essentially now you have this cation can hop into this this vacancy, and you can have an anion hop into this, and in the same way these vacancies can move around in coupled pairs, right? So I don't want to get too quantitative about it, but if we think about the rates, right? We already said that the activation energy for ionic solids is higher than that for metals. Let's think qualitatively about why, right? So what did we say about the energy to form a Shotkey defect versus the energy to form a vacancy in that homework assignment? Right? Anybody? Oh, come on. Somebody has to remember.
Just so you know, I'm not answering. I've decided that for the 3 classes, I'm not answering anymore. Or maybe the next classes, we'll see.
Okay, come on, somebody else.
I'm done putting my behind on the fire.
Everyone appreciates you for it, Kevin. Oh, come on. Okay, well, the awkward, embarrassing Friday silence then. So it's about a factor of 2, right? So what does a factor of 2, right, when we have our exponential here, that gets pretty significant, right? So that's just the defect part, right? What about the migration part? Right? Does it seem in a metal, right? If I'm on a simple cubic lattice in the metal like I was before, right? I have jumps that are seem pretty easy to make, right? Because I don't have a huge amount of hindrance. However, depending on the ceramic structure, it could be really hard, especially for anion jumps, right? To move things out of the way. I've got this big anion, and it has to squish a bunch of stuff out of the way. So in general, the enthalpy of defect formation and the enthalpy of migration are both going to be significantly higher for Shotkey diffusion, right? And if we put that into the exponential, right, a factor of 4 here, right? I mean, if we think about it, you know, that corresponds to more than an order of magnitude difference, right? A factor of 4 inside this exponential drops our overall diffusivity by 1.5 orders of magnitude, right? So what about I have another defect here. These are Frankel defects, right? Has anyone come across these before? All right. So depending on the cation anion size, this ratio, right, and charge, you may not actually be able to form these anion vacancies very easily. It might be too expensive. So you then have a situation where you have cations that instead of forming these paired vacancies, you have cations that go interstitial, right? Leaving a vacancy behind, right? This is interesting because obviously Frankel defects were named after Frankel. He was a Russian scientist in the 20s. So this mechanism was theoretically developed long before the notion of Shotkey defects. And this was sort of one of the first fundamental theories of defects in ceramics. But Frankel defects, a similar type of energy level to Shotkey, right? And so we can just take a look here at this is essentially the temperature dependence of the diffusion coefficients for some common ceramics. And we see that this is a log scale, of course, right? And this is 1 over the melting temperature.
So, question.
Yeah.
So basically the ones with the steeper slopes will diffuse faster?
So the ones with the steeper slopes have a much stronger temperature dependence, right? So that means you don't need to increase the temperature as much to increase the diffusion rate.
That's kind of meant, like if you have like a material and you're heating it up, the faster ones will have.
Yep. Right. And so, but what's interesting here is take a look at the range. This is what I wanted to really highlight here, right? Of diffusivities over in different ceramics, right? So we go from fairly fast ion conductors, right? Like this calcium zirconium oxide, down to 10 to the minus 15th, like uranium and uranium oxide, right? So we have here 9 orders of magnitude range in the diffusivities, right? We don't see anything close to this in metals, right? So what this tells you is that ions can move fairly fast in some ceramics, fairly slow in others, right? This shouldn't be too surprising, but what it tells us is that there's a strong relationship between the diffusivity in ceramics and the rate of ionic or electronic conduction, right? Most of the time we think of ceramics as insulators, right? Because if we have a structure like this, how are we going to move electronic charge, right? We know that the band structure is such that we don't have any we don't have any electrons in the conduction band, right? So really the only mechanism for electronic conductivity is going to be the movement of ions. So electronic conductivity and ionic conductivity are intrinsically coupled in ceramics. And talking about that in great detail is beyond what we want to do here. But what's important to realize is that it's the diffusivity of the ions is directly related to the ionic conductivity, right? Of these mobilities, right? And it's going to depend very much on the concentration of these defects that are going to be there, right? So this is the ionic conductivity is a function of temperature, and you'll see that you've got the slopes and relationships that look very much similar to what we see in terms of the diffusion coefficients. There's a direct proportionality there. Okay. So we have some other defect mechanisms. Some of these appear in metal, so we have die vacancies, right? Die vacancies are exactly what they sound like, right? At close to the melting temperature, it's actually energetically favorable for two vacancies to come next to each other than it is for two separate vacancies, right? But this is really only at very high temperatures when the vacancy concentration is fairly high, right? Now you can imagine that this then becomes quite complicated, right? Because if there's an energy gain to keeping the die vacancy, essentially it means that there's a penalty that comes into play. We don't want two atoms hopping into both empty vacancy slots at the same time, because then they pull apart, right? So yeah, so Dagny, you've got it, right? It's essentially it's like a surface energy type argument, right? That you're effectively forming little holes, and as you get closer to the melting temperature, you're forming essentially little pores, right? Rather than just individual vacancies, right? It's a really an interesting area that needs to be explored more, right? But yeah, we can totally think about it that way. Then we also have an interesting mechanism in metals, which is sometimes called the interstitial seam mechanism or self-interstitials. So this is where a atom jumps off its lattice site into an interstitial site. And you tend to get this like dumbbell configuration, right? So here's an atom on the lattice, here's a self-interstitial. It has to move some other atoms out of the way, so we get these two that are packed really close together. All right, and this is commonly referred to as the dumbbell configuration. And the mechanism here is essentially like billiard balls, right? As an atom, as the atoms vibrate, they push against each other, and you'll push this chain of atoms. This will move into this interstitial site. This one will move out right into here, right? So we've got this interstitial atom hopping onto a lattice site. This lattice atom then gets bumped into another interstitial site, right? So it's like this chain of atoms pushing each other. So you can imagine that this is much higher energy than vacancy diffusion, but it does occur. It's another mechanism that happens. Okay, so all of what we were talking about before, right? For Fick's first law, we said that there's a concentration gradient, but we didn't have a chemical potential gradient, right? So if we had an initial concentration gradient and all of the jumps are equal probability, just from the fact that we had more atoms on plane 1 than plane 2, we had a net migration in that way. And eventually everything would become homogeneous. The jumps wouldn't stop, but on average we would have the same number of jumps from 1 to 2 as from 2 to 1, right? So everything reaches a steady state. When we're in a chemical potential gradient, that's no longer true, right? The analogy of the bar on a steep hill in San Francisco is that all the stumbling drunks end up down in the valley, right? Except for a few that go up the hill, right? So we want to think about and analyze this situation. The book does an exceptionally poor job, I think, of talking about this. It makes it overly complicated, I think. It's really straightforward just to think about, we have a situation like this. This is our chemical potential gradient. Remember, chemical potential is just a partial molar Gibbs free energy, right? So we can think of a chemical potential gradient as being this gradient in the Gibbs free energy space, right? And that if I have a jump this way, I have a net lowering of my Gibbs free energy, right? If I jump this way, I have a net increase in Gibbs free energy, right? For this particular atom, the per atom free energy, right? Now, that in and of itself, if we think about, trying to optimize our energy, that in and of itself is going to make things go this way, right? It's going to say the system's going to try and find the minima, but it's actually biased even more, right? Because right now, if I'm in this site where my atom is, and I'm jumping to this site, my activation barrier that I have to overcome is my delta GM, right? That doesn't change. But if I'm going the other way, now my activation barrier is my delta GM plus Xi, right? My change in chemical potential, right? So if we think about our Boltzmann statistics, we know that the frequency, the atoms that have enough energy to overcome the barrier, right, is in that exponential term, which means that when we looked at the energy for nucleation in the homework, right, we saw it was essentially a step function. Right, so a fairly small change in the energy barrier for a given temperature means that either it's going to happen or it's not. So most of the time, right, which means, let me be clear, this chemical potential gradient is usually fairly shallow, right? So this Xi term isn't a huge barrier compared to delta GM, but we don't need a huge barrier, a huge addition to this barrier to make a very large effect, right? So we're still going to have atoms jumping this way, but we're going to have a much, much smaller fraction of them going this way than by going this way. So that means a fairly small chemical potential gradient is enough to make to bias the diffusion one way in the other, right? And so we can say the force, the driving force for diffusion in a chemical potential gradient is going to be directly proportional to that gradient. Right? So this chemical potential change in chemical potential is directly related to our driving force. Right? So this is why chemical potential was such an important and useful concept, right? It tells us exactly which direction mass transport is going to happen in our system. Just like the voltage tells us exactly which way charge transport happens in our system, and the temperature tells us exactly which way heat flow passes. I know I sound like a broken record when I keep defining chemical potential, but I want everyone to be really clear on this concept. It's not some magical, mystical thing. It's just a gradient in free energy that tells us which way things are going to move. Right? Okay. So what do we say about our net jump frequency? Well, our net jump frequency is just going to be our forward direction minus our backward direction. Right? So we just essentially do what we did before, right? We have the forward minus the backwards. We do a little bit of algebra and rearrange, right? And now we have this term. And as I said before, chemical potential gradients are fairly small compared to delta Gm and the thermal energy available. So that means we can use the small, the approximation for small x in our exponential relationship, and we get an expression like this where we can put the gradient out front, right? So the diffusivity in a chemical potential gradient looks exactly like it was before. We can keep our D naught is still the same D naught that we had before, but now we just have an extra term that's our chemical potential gradient, right? And when our gradient is 0, this term just becomes 1. Right?
I got a question.
Sure.
So I'm thinking of like a copper crystal, like a wire.
Okay.
With the electrons moving through it. And does the electron charge, positive or negative, affect at all the amount that one atom would move from one place to another? The vacancy, any of these equations, essentially would charge affect it?
So, okay, to a first order approximation, the vacancy is charge neutral in metals, right? There's a small effect, right? Because we're disrupting the electronic structure right there. That's not a super accurate approximation. But to a first order, we can say that, right? So that what that tells us is that in general, when we're thinking about diffusion in metals, that the electronic effects, the electronic conduction is happens on a much faster time scale than diffusion, so that we can say, since the vacancy is approximately charge neutral, the time scales are far enough separated that the electronic conduction is not going to affect diffusion, right? But that's a first order, very much a first order approximation, okay? It gets complicated whenever you have a electrochemical potential. Then in metals, things get different. I'll let Professor Frankel talk about that, or Professor Locke if you take the advanced, the corrosion class, right? But an electric current does do weird things. There's an effect that's not really understood very well in my primary area of plastic deformation, that if you pass an electric current through hexagonal metals in particular, you get an alteration of the flow stress that's different than if you just heated it up to the temperature, right? So you get joule heating in your wire or your plate, and you activate different slip systems than would be predicted if you didn't have the electric current. Why that happens, it's really a huge area of debate, and there's lots of theories that don't make a lot of sense to me personally. But the moral of the story is that an electric field does do weird things that you wouldn't initially expect. So will the diffusion be exactly the same? No. But for the purposes of thinking through problems and trying to understand what happens, yeah, just you can make that approximation. Okay. But getting back to it, right, the main thing is just we have to explicitly consider this chemical potential gradient directly. And this is what provides the driving force to move against the composition gradient, right? When in the examples that we showed, when we have a miscibility gap, this chemical potential gradient becomes large enough to bias our jumps so that we have A can move in the direction of the A composition, right? And get more concentrated. Okay. So your book the reading talks about this in terms of atomic mobilities, right? So this is, I think, sort of very fundamental theory, and I don't know why your book doesn't talk about this. Instead, they talk about drift velocities and net fluxes. So if we have a composition of A and a drift velocity, we get this flux. So what this tells you, if I have atoms moving through a planar surface, right? If my paper is a planar surface, my net flux can be balanced by two things, right? Either I can have a large number of A atoms moving through this plane, right? I have let me just be clear. I have A atoms moving this way, right? Right? So A atoms moving this way. My net flux can either mean I have a whole lot of them, a whole lot of A atoms, and they're all moving very slowly, or I can have a smaller amount of A atoms here and they're moving very quickly, right? And what your book does is it develops a relationship between this velocity of the atoms and the chemical potential gradient that they're sitting in. Basically, that the higher your chemical potential, the faster the atoms are going to be moving, and this proportionality constant is going to be something called the mobility, right? So that means your flux is going to be your atomic mobility times your concentration times your chemical potential gradients. So then it does something that's theoretically correct, but I think a little confusing, especially for students seeing this the first time, right? It works through the regular solution theory, right? And puts this chemical potential here in terms of the activity coefficients and rewrites the diffusivity in terms of the activity. Right? So this is really useful if you're looking at the Gibbs free energy curves, but it doesn't help you intuitively think about what's happening in a system, right? So the mobility is kind of an important concept, but it's not a really useful one. It's much more useful to just think about it in terms of this way, right? We've got the diffusion law that you've seen before, D naught times the exponential of the activation energy for diffusion over RT, right? This doesn't change, but we just have an extra term here that describes the chemical potential gradient. And the stronger the chemical potential gradient, the more this is going to bias it, right? And of course, these activity coefficients are directly related to the chemical potential. We spent some time going over that when we talked about our regular solution theory. Right, but this is just, it's not an intuitive picture, right, at all, I think, right? This is just much clearer and cleaner, and unfortunately, this equation doesn't appear anywhere in your textbook, right? And so that's where I wanted to wrap up for today. So we'll finish a couple minutes early. That makes up for stealing time for you on some other days, right? So anyone, any questions or concerns or?
So what would you say is the key formula to take from all of this?
Right here. This is the equation, the diffusion equation you want to keep in your head.
Okay. And
I've got a temperature independent pre-exponential term out front, right? I then have an activation energy that I have to overcome, right? This activation energy is is independent of temperature as well, but the probability of overcoming it is going to depend strongly on the temperature.
okay, and what is this one symbol, like the weird symbol over the RT again? Like that's
This here, this xi,
yeah.
right? It's capital Xi, but this is our chemical potential gradient.
Yeah, I was like that's why do we? I guess before you just use chemical potential, not the gradient. Okay.
Right. So this is it's actually chemical potential over the jump distance.
Got it.
Right. Right, but it's just this extra energy that we have to overcome due to going up this gradient here, right? So it's a free energy, right? But it's just because we're in a chemical potential gradient, it's the extra free energy that biases the forward direction from the reverse direction.
So basically, this is the reason why diffusion will occur more in one direction, or why it would occur when there's not much of a temperature.
Yeah. So this tells you, right? So even if this is one, right? If there's no chemical potential gradient, right? You will have diffusion that will make the concentration uniform everywhere, right? What this term does is explains the driving force for a net flux, right? Transport chemical segregation in a system, right? So this tells us when we're in that our looking at the common tangent construction, right? When we're in between our two concentration minima, right? Why we're going to segregate along into those phases given by the common tangent, right? This is the driving force to do that.
Got it.
Okay. So this is, I think, the most important equation, right, in all of diffusion. And I said, you know, remember at the beginning of the year, I said there's a couple things I expect you to know, right? So, you know, it was the common tangent construction, Scheill's solidification, and the temperature dependence of diffusion, right? This is it, right? This is the one thing. There's two things for diffusion that you have to think about, right? One is the length scale is going to be square root dt, right? The distance that diffusion is going to occur over for a given time is given by the square root of dt, right? So that's the time dependence of diffusion. This is the temperature dependence of diffusion and the compositional dependence, right? So it tells me based on my local conditions how fast that diffusion is going to happen. Right? So you can just put a big star next to this, right? And write no for final. But thank you for asking that question. Anything else?
Speaking of the exams, I had a few questions regarding that.
Sure.
First of all, in the chat earlier, it was asked, it's on Wednesday, correct?
So I will be putting it up on Carmen on Wednesday.
Mm-hmm.
And then you do it at your leisure and turn it in on Monday.
That was my next question. So it's the completely take-home format. We have the exam and we...
It's completely take-home. And I'm giving everyone a heck of a lot more time than you need because I know that this is not the only class you have, right? So I don't want time pressure to be an issue with the exam.
Okay, and a question just came in the chat. Are we going to have class on Wednesday and Friday?
Yes. Yeah. Right? So you'll still have normal classes, right? Again, that's why, you know, again, I'm giving...
If you're giving us 5 days to do the exam, I think we can manage to spare a couple hours for class.
A couple hours of class, right? And I'm holding off on any homework or reading assignments until after that, right?
More than reasonable.
Right. So, in terms of what's on it, the exam is going to cover the first 4 homework assignments, right? In terms of content.
Last question regarding the exam. Then I'll be able to go today. Will we need to do a lot of value research on the exam like we do for the homeworks? Not a lot. Okay, just understand that maybe like if we set our sources, that certain places will give us different values than what we're looking for.
Yeah, exactly. Right, and I want to sort of avoid that. In what I want is the exam is I want you guys to be able to demonstrate what you understand about the material, what you understand about the physics, right? Looking things up in the homework is because I want you guys to develop that skill, right? But I don't want your exam grade, right, which is purely about applying the material, right, and thinking about the material. I don't want that to be a hindrance to get in your way, right? So there might be something that you need to look up, but it shouldn't be anything onerous or difficult, right? So No, the exam is not timed. I'm just putting it up on Carmen Wednesday sometime Wednesday after the lecture. And it'll just be open on Carmen. It'll be turned in just like a homework assignment on paper.
However, because we are giving you the full 5 days to do it, please make sure you turn it in early, because we really don't want to hear at 11:59 that you have computer problems.
Yeah. Yeah. Right. So, yeah, thank you for bringing that up, Alexander, right? Yeah, you have plenty of time to do it, right? So that means my patience for late exams will be very, very small, right? I've been pretty generous with people who have contacted me and have needed an extension on the homework. But there will not be extensions on the exam except under really exceptional extenuating circumstances. Right? If you're in the hospital, right? You know, things like that. Right? My computer crashed 5 minutes before the class started Monday morning is not a good excuse to not getting the exam in on time.
I have a quick question about like the mastery questions. Is that like still going to be a thing? Because I have never been able to find anything about it.
Yeah, so the mastery questions is just turned into this giant mess of me trying to get them to work right. Right? So, I still want to have them there, but no one has not missed anything. And what I may have to do is, after the exam, basically just give some people not some people, assign to the class sort of much more straightforward, just calculation-based questions, right? Which is what the mastery questions are supposed to be. The homework questions are supposed to be more difficult to help you, that you think about the concepts, right, in a deep way. The mastery questions are supposed to be easier, more plug and chug type questions to just help you practice the mechanics. Right? So if I can't get them working on Carmen correctly, I'm just going to give a sort of a paper assessment, right? And the mastery questions are not graded like letter grade. It's graded, did you do them or not, right? Did you get them correct? So don't worry about them between now and the exam, but they haven't disappeared. They're just with this transition. I'm learning a lot of new stuff, but it has not been easy. Trying to get open-ended mathematical questions to work properly, right? You saw how badly it went with the reading quiz, right? That one time. So, okay, anything else? Cool. Have a good weekend, everybody. We will see you on Monday. And take care.